And hi, everyone. We're live. So good morning, good afternoon, good evening, whatever time it is for you. My name is Jim Pfister, and I will be the moderator today for What is Confidential Computing and Why Should I Care? This is a presentation of the Storage and Networking Industry Association Cloud Storage Technology Initiative. And we will be here for the next hour talking about confidential computing. We have a wonderful intro screen, but what I actually like to do is show everybody off in the video. So again, my name is Jim Pfister. I will be your moderator today. Hopefully I'll be staying out of the way of three very intelligent people. Let's introduce ourselves. So David, why don't you start and introduce yourself?
Yeah, hi, I'm David Kaplan. I work for AMD and I'm a security architect. I focus primarily on confidential computing technologies, including AMD's offering in that space called Secure Encrypted Virtualization. And yeah, I'm excited to be here. Been working on security for probably about a decade now.
All right. Ron, why don't you go next?
I'm Ron Perez. I'm a fellow at Intel, where I sit in the data products group, which is kind of the data center cloud-focused part of Intel. And I'm responsible for that part of Intel's organization's security strategy, roadmap, the various technologies. Lead a group of fairly senior technologists who are all security architects looking at developing confidential computing technologies.
Excellent. And Mike, how about you introduce yourself?
Yeah, hi, I'm Mike Bursell. I'm a co-founder of the Enarx project, which is an open source project around trusted execution environments. And I spent the last very nearly 5 years in the office of the CTO at Red Hat as chief security architect.
Oh, excellent. All right. So those are your experts for today. Let me do a little bit of housekeeping for you. So first of all, you who are listening, thank you for listening, by the way. You have a couple of controls underneath your viewership screen. First of all, there's one in there that will allow you to blow everything up to full screen, and you have the ability to do that. We'll mostly be talking today. You won't see a lot of slideware. The slides are available on the download tab. And I believe also in that download tab is a link to another upcoming presentation, and we'll talk about that at the end. Let me spend just a minute on what the Storage Networking Industry Association is. We are 180 industry-leading organizations together in a public industry body. We have 2,500 active and contributing members, and we reach out to about 50,000 IT end users and storage pros worldwide. We've focused on developing standards and delivering open opportunity for the industry. And what we want to do is educate, support, and promote, understand, and collaborate with the industry in order to be able to advance technology in the industry and essentially float all boats. This is a copyrighted presentation of the Storage Networking Industry Association. Just, you know, we want to cover a little bit of legal. I checked. None of the four of us are lawyers. We are not intending to give you any legal advice here. And this should not be construed as legal advice or opinion of counsel. Obviously, you'll be hearing a lot of personal opinions and current understanding of the relevant issues involved. But we're not assuming any liability for that. So let's talk about what is confidential computing and why should I care? So why don't I start with that? And David, I'm actually going to go to you. So start with what you think confidential computing is, and how did this all begin? What's your view of why and why it was needed?
Yeah, so confidential computing is a new kind of security paradigm, I would say, that is useful in a number of cases, but I personally like to talk about the public cloud case. To me, that makes the most intuitive sense. And that's simply because when you have an environment like public cloud, you want to run a workload on somebody else's system that you may not trust. And you want your data to always be protected. And confidential computing is a technology that can enable that. So it can enable you to run a private workload, whether that's sensitive corporate data, health information, and so on a system that you are not the administrator of. And this provides something that we in the confidential space like to call data in use protection. So we've traditionally heard about things like hard disk encryption, storage encryption. That's what we typically call data at rest. We have good solutions for that, and those are great. those complement confidential computing technology, because confidential computing enables that data to be protected even while it is off of the storage medium and it's being actively processed. So that's, I think, maybe the 1 minute summary, and I'm sure my colleagues will be happy to fill in the gaps. So
Mike, what would you add?
Yeah, sure. So, I mean, I go back to the Confidential Computing Consortium. So that's an open body. It's a part of the Linux Foundation. It's about encouraging open source use of confidential computing. And their description, their definition is confidential computing is the protection of data in use by performing computation in a hardware-based trusted execution environment. So touching a bunch of the words that Dave has already used there, I think the important thing here is that we're protecting the data, not just with software, which might be at the danger from compromise or malicious actor, but actually using hardware. Typically, I think we're going to be talking about CPUs here, but maybe we'll go talk about later on. But CPUs protecting. So even if you have kernel access, even if you have supervisor access, admin access, hypervisor access, you shouldn't be able to look into that workload, that application, that program that's running. So that's how I put it. I think that the hardware protection is a really important thing here. Ron, what do you add to that?
Yeah, no, that's excellent. I think you guys covered the whole space of what confidential computing is, right? Which is great. It's good that we all agree. And maybe I'll address the second half of your question, Jim. You're talking about where did it come from, right? Sure. Like everything in computer security, right? There's a long, rich history that goes back many decades, right? Probably a lot of the seminal work in computer security was in the 70s and 80s, right? But not going back that far. Let's say I would probably draw the linkage to a lot of work that was done both in kind of purpose-specific areas like embedded systems, gaming consoles, right? With the Xbox, the Sony PlayStation, right back in the late 90s, early 2000s. Hardware security modules, right? Another example of a purpose-specific device, right? That had this protection of data in use concept, right? TPMs, right? The trusted platform modules, and those loosely associated, right? But all those together, I think, as well as some fantastic work in academia, right? Just to name one, right? There's kind of a series of developments that happened with Srini Dividas' organization at MIT, with Ascend leading up to Sanctum over many generations, right? All in this space, right? So everybody really pushing the boundaries. I think the industry finally recognized probably in the early 2000s or kind of mid 2000 up to 2010 that there was this need, right, especially as cloud really started picking up. And I think that's where we started to draw from all these experiences into a lot of the capabilities that you see today, whether it's with Intel's software guard extensions, right, SGX, or David mentioned AMD's SEV, right? So and in similar technologies, ARM, right? ARM with their history in the embedded space, right? Trustzone was one of the first trusted execution environments available.
And I'm not an ARM employee, I should be pointing out, but ARM have announced ARM Realms as well, and IBM have PEF, which is Protect Execution Framework, I think. You mentioned an important thing there, Ron, which is TPMs. And I sometimes hear people saying, surely this is just what TPMs do. And I think it's useful sometimes to draw a distinction, because we usually use TPMs as a root of trust in a system, and you can do some execution in a TPM, very specific crypto functions. I think the important thing here about TEs is they're about generalized computing. You're not having to do just crypto stuff. Of course, you can do crypto stuff in them, but it's about generalized computing. And TPMs and TEs may well have complementary uses in the same system or set of systems, but they're separate things.
Good point. And I think another Another
I was going to say, you mentioned TEE. I just want to make sure that that we define that because we haven't talked about that.
Trusted execution environment. Trusted execution environment. So it's a phrase which we try to use, particularly in the Confidential Computer Consortium, because we want to avoid talking about ARM realms or Intel SGX or Intel TTX or AMD SEV or anything. It's the general term across the industry. Trusted execution environments. Sorry.
Okay, go ahead, Ron. You were going to say something.
No, I was just going to add one more thing on the TPM where I think the connections are maybe more obvious, right? So Mike was really good kind of drawing that distinction, right? But TPMs probably were, and again, this is not a new concept, but TPMs certainly established attestation, right? As a very strong need, right? Attestation is basically a verifiable report of what's running or what's been so-called measured, right? Basically, you want to know what is actually on the system that you don't have direct access to, right? That you're accessing remotely, right? And TPMs kind of were really at the forefront of establishing formats and protocols and expectations, really.
We should talk about attestation in a bit. I think we should. We need to explain what we're doing first, but attestation is a really important bit to be. You're quite right. But TPMs do tie in.
Yeah, and I agree with you, Mike. Let's actually talk about what we're doing. So let's talk about what goes on under the covers in a trusted execution environment. So, David, why don't you start with that as well?
I'm feeling I was going to get that one. Yeah,
you just haven't talked in a while.
Well, everyone's so chatty. What can I say? So what goes on in a trusted execution environment is essentially hardware enforced isolation. So you have a workload that you want to isolate from everything else in the system. And you might actually have multiple of those workloads that each belong to different customers that are all sitting on the same piece of hardware. And within that trusted execution environment, you're doing computations, you're doing memory accesses, you're doing IO, things like that. And what the hardware is doing is it is making sure that nobody else is able to access the data that you're working on. So that means all the other customers that are on the system, the administrator of the system, like if there's a hypervisor, they're not able to access it. If there's IO devices, they're not able to go and poke into what you're doing. And so that hardware layer is enforcing that isolation. It sometimes does that with encryption. So it might encrypt the contents of memory. So if somebody reads it, they just see junk data. It might enforce it with access control. So somebody who tries to read or write the data is denied. They get some sort of a hardware exception. And those sort of things vary by implementation. But the basic theme is that the hardware knows when you are in your TEE or if you're outside of it, and it enforces that isolation. And it does so in a way that even if the software is compromised, you still get that enforcement.
So back in the day, that was how we were describing a TPM. We were basically, well, this is a blob and you can't look into it, so it's got things.
Yeah. So
how is that complementary?
The difference here is that what you're taking is standard memory RAM on the system and encrypting pages.
Yeah, and maybe I can expand on that a bit too, because there's different types of isolation. And the simplest form, if you will, is physical isolation. And that's kind of what you get with TPM, where you actually have a separate physical device. I mean, at its simplest level, if I have two physical machines and one runs my web server and one runs my HR, that's great. They're physically separated. There's other forms of isolation too. You can have temporal isolation. You can run one workload, then you stop, and then you go and run something else. But what we're dealing with TEEs is either logical isolation, so we prevent access from one to the other, or cryptographic isolation, where we use cryptography as a tool to enforce that isolation. And those are great because modern processors have so many capabilities, they have so many resources on them, and we want to use all those at the same time.
It comes back to the generalized compute, right? It's general compute. Yeah.
We want to run hundreds of customers' workloads at the same time in a way that is completely isolated.
Can you have a TEE without a TPM in the system?
Oh, yeah.
Absolutely.
Oh, yeah. Okay.
Yeah, no problem. Yeah. So one interesting, actually, Ron, did you have something to say that? I had an interesting thing, I think, in the cloud space, but did you have something?
I was just going to add, hopefully what David and Mike said already should be powerful enough, right? But maybe to draw that distinction a little bit more for those of you maybe less familiar with the technologies, right? What we've traditionally done in computer security is kind of I'll call it a stack-based approach to security, right? Everything is layered on top. So if what you're concerned about is your application, or your code, and your data, you're relying on probably some application framework, maybe some middleware, a huge operating system, a hypervisor most likely, and firmware in the system of all different types, right? So there's this huge, what we call a trusted computing base, right? Everything in the system that you have to trust to protect your code and your data, right? Even if that's only a few lines of code and a few bytes of data, right? The power of confidential computing is saying, no, it turns it around. It says, now all you have to trust is your code and your data and the hardware. All that software, firmware, software, et cetera, literally millions of lines of code, right, in between your application and your data, right, and the hardware, all of that you don't have to trust. And the challenge is, actually achieving that, right, with modern general purpose hardware.
Mm-hmm. So the thing I was going to add, all yes to that, of course, is that one of the interesting things about confidential computing from the cloud point of view is that we're used to being able to shove loads and loads of workloads onto a single machine, and which is great. Part of the reason we can do that is because quite a lot of the pages, memory pages, on a standard set of workloads are shared. You've probably got the same kernel pages, a whole bunch of other pages. So you can actually share memory pages, which are read-only pages between workloads. That doesn't really work when you're doing confidential computing because each page is encrypted for that particular trusted execution environment, which means that the density of workloads on machines where you're using trusted execution environments in confidential computing is likely to be lower than a standard computing case.
Yeah, that's true, but I'm not sure it's significantly lower. It depends a lot on the workload. The amount of data that you can share is likely going to be limited to things like the operating system image, which honestly is not all that big if you're also running a multi-gigabyte database. So you're definitely correct. There are some trade-offs, right? There are some performance optimizations. There are some other things that you can't get, at least with the current generation of TEEs. But I think that for a lot of workloads, you're not going to, maybe there's some density impact, but I don't think it's going to be all that significant.
Yeah, no, I think that this kind of draws the importance back to David, what you said early on, how you focused on cloud computing, where the real value of confidential computing is realized, right? And it's because of that sharing, right? Cloud, the whole value proposition about cloud computing is sharing resources for efficiency, right? And of course, the enemy of security is sharing, right? For the most part, as we live it day in and day out, right? Whenever you share resources, whether it's a CPU, memory, operating system code, whatever it is, right? You're bound to have security issues, right? If you're not really, really careful.
Yeah, and actually, sorry, if I can just add one thing onto that, to bring it back to sort of the initial question on sort of why are we talking about this today, right? Why didn't we talk about this 10 years ago? I think that the rise of public cloud and the popularity has been a driving factor in this. There are so many advantages of cloud, scalability, affordability, and so on. And the cost of that comes with a bit of a loss of data sovereignty, right? You're putting your workload on Amazon or Google or whoever, and confidential computing is a way to gain back some of that control of your data. And so I think that's one reason that we're having this conversation today. And
I think I'm going to do the golden boy here and bring us to storage, because this kind of storage is important. I know the forum we're in, because we're talking about cloud, we're talking about cloud storage. And where does it fit in? How does it work? I think there's some interesting stuff here. First of all, I think you mentioned at the beginning, David, that we've known how to do encryption at rest for a while. That's storage. You know how to do encryption, in motion. That's transport for a while. But it's this encryption in use that confidential computing brings to us. And I think one of the struggles that customers have had around cloud storage, or let's rephrase that. Using storage from the cloud might be another way of looking at it. Is that it's very difficult to secure it, because yes, you can encrypt stuff in the cloud. You can encrypt, stored data in the cloud, but where do the keys, the cryptographic keys to do that encryption and decryption live? And the answer to that is, unless you are keeping those keys on your internal servers and locking them down really tight, it means they're actually running themselves in the cloud, which means that your cloud service providers or anyone who compromises those servers or your workloads can see them.
Yes, and the other thing which I think you're getting to shortly here is, how do you know if, let's say you have a password for your storage, how do you know if you're providing it to the correct entity?
Yeah, absolutely.
It comes back to the A word.
Yeah, so we can, what that means is that we can now start actually using data and saving data that we are using in the cloud much more safely. So cloud storage can be much closer to the safe places. I think that's a really, really important way of changing how we think about how we architect the workloads and how we attach the storage remotely, locally, or however you're doing it in that sort of way. Sorry, Ron.
Well, one of the things I always like to, I want to take this in a slightly different direction. One of the things I like to look at is, well, what are the guardrails that you're operating in? I mean, and Ron, you talked about you want to only trust your code, or in some ways what you might, there might be some people out there, it's like, well, I want to run everything in that TEE because I want to be able to, control my own domain. So Ron, you mentioned with confidential compute that you only need to trust your own code. Is there a danger of a hardware attack that can actually break that TEE isolation? That would be the first question that I would ask. And then let's get back to, so how do you decide what you're going to run in the TEE versus not?
Yeah, it's an excellent question, right? And there are certainly different types of TEEs that support different abstractions, right? Whether some support the VM abstraction, where you put your entire virtual machine and all the applications into this trusted execution environment, right? And that's fantastic, right? Because the vast majority of cloud workloads out there are based on VMs. That's kind of the unit of deployment, right? So you can just pick what you have today, whether however legacy it is, right? Plop it into a secure VM and call it a day, right? But there's also a slight risk, I would say, of being overly confident in that, right? Because if you have bad code in your VM to begin with, in your legacy application or in the operating system itself, right, it's still going to be buggy or bad code, right? Even though it's protected in a trusted execution environment, right? And there can still be other exploits, traditional software exploits, buffer overflows and whatnot, right? So on the other side of that spectrum, from putting an entire VM into a secure container, if you will, right? There's the other side of the spectrum is how fine grained can you go, right? And a lot of people would very much like to only have to focus on those pieces of code and that data that really needs the protection, right? Sometimes it's just a key, a cryptographic key, right, for protecting your database or whatever it is, right? Sometimes it's, think of like the U.S. Post Office, right? They have a very simple algorithm, whatever the cost of the stamp is, right? They deduct that, whenever you issue a stamp, right? Very simple algorithm, but very important to protect that algorithm, right? It has to execute correctly, right? Every time, just as an example, right? So it may be a piece of code that's that insignificant, that small, but it really has to be protected, right? So you'd like to have, the spectrum of capabilities, right? And we're seeing those, right, with the number of different technologies, trusted execution technologies, right? Some that are very fine-grained, maybe they allow you to kind of scale up, right? Others that, are more coarser-grained, but address, 80% of the market, let's say, right?
Well, David, Mike, what would you add to that?
Yeah, I just want to add, I mean, Ron's completely correct. And there's sort of, a general principle in security that the more code you have, the more chance there is for bugs. The bigger the attack surface, the more interfaces you have, things like that. And confidential computing is already about reducing the amount of code that you have to trust. And if you take a traditional server system today, you've got a hypervisor, you've got all kinds of drivers. Those are all pieces that, if compromised, completely break down all of the isolation within that multi-tenant server. So confidential computing is already saying, put all that stuff to the side. We don't need to trust that. But then still, you have the code that you run within the TE. And what Ron's basically saying, which I agree with, is that the more you put in there, the bigger the risk there is for bugs. And so there are a variety of different deployment options. And I think there's ones being developed every day to take advantage of hardware TEs at all different levels. Putting an entire VM is probably the easiest option just from a deployment standpoint, but having some very, very small custom code where you only have the things that you need to trust in there, that is going to be more secure in the long run.
Yeah, and I think there's sometimes a misunderstanding about what VM means or what it can mean when we're talking about TEs, because you can kind of separate the approaches that manufacturers have taken, the silicon manufacturers have taken, into process-based, SGX being a good example, or VM-based, AMD SEV being a very good example. But when we say a VM, that doesn't need to mean an entire BIOS, OS, all of that sort of stuff.
Right.
A VM just means a virtual CPU and at least one memory page, right? So it's actually possible to build a very small operating system or runtime environment within a VM without pushing all of that stuff in. So, I mean, I'm going to plug my own project now. The Enarx project does exactly that. So the Enarx project aims to abstract away the hardware layer. So we don't feel you should care about whether using SGX or SEV or future stuff that's coming out, because we provide a WebAssembly runtime which works very closely with whichever hardware abstraction we're running on. So we don't put in a BIOS. We've written our own syscalls, we've written all those, a microkernel, all those sorts of things. So which I think just adds to the spectrum, right? There is a very broad spectrum of different things you might be adding and putting in.
And that leads to an interesting question. And there was a question from the audience, so I'm gonna kind of co-opt it. But the question from the audience was, how do the various virtualization environments currently handle confidential computing? But you were just talking about Enarx, and then we're also talking about members of the Confidential Computing Consortium. What is the Confidential Computing Consortium doing to enable the broad virtualization providers like VMware, like Nutanix, to be able to use confidential computing?
Yeah, well, VMware is a member, as is Microsoft, as is Google, as is Red Hat. So some pretty big folks in there, and Facebook and other folks too. So the approaches people are taking are vary. The cloud providers are doing their own things as well. So you could go right now and take a very basic low-level VM in the way I talked about from someone like Azure or Alibaba or Google or whoever it may be, or they also have frameworks to help you to get into that. There are some interesting security issues about that, because most of the cloud providers are really interested in making sure that they're in that trust relationship, which is maybe not such a good thing. So, for instance, if you want to put your own full VM into a cloud service provider VM, they may put the BIOS in there for you. And you've immediately got to ask yourself, is this really what I want to be doing? So there are some interesting things. I think this market is going to be maturing over the next 18 months or so. We're seeing some really interesting startup stuff going on there as well. So it's difficult to give a survey right now of what the different options are, but certainly all of the major people in the space are looking at how to roll this out. And for bleeding edge early adopters, there are some opportunities, and we're seeing some very interesting stuff happening out there.
Yeah, and I just want to add to say that it is very early right now when it comes to deployments of this stuff. I mean, the technology has only existed in hardware for a few years. It's not a trivial thing to implement. So, we're starting to see some previews, I know, from some of the major public clouds, but it's very early. I would say that, maybe there's kind of two general directions of things we're seeing, right? One is the full VM isolation, which is, ideally you take your existing workload and you sort of check a box and now you get some more security. And then another is more of a container based solution. But yeah, I would say, stay tuned. I expect a lot over the next couple of years.
Yeah.
Yeah, that's a good point on the containers, David. And Mike, to your point, right? I think we're seeing workloads in general evolving, right? With containerization, function as a service, right? Certainly workloads are getting more heterogeneous too, right? We haven't gone there yet, right? We've been talking mostly about CPUs and virtual machines and, trusted execution environments that are CPU focused, right? But we're seeing, workloads get much more heterogeneous using GPUs, FPGAs, right? Other acceleration devices, right? All of those will need to be encompassed in confidential computing, at least from the security properties perspective, including, in storage compute capabilities, right? Bring it back to SNIA.
And when Adam says this is, sorry, Adam and David says this is difficult stuff, this is it. It's not just the technical putting it on the chip stuff, it's actually building it together in ways that you can prove and have assurances and cryptographic proofs that what you're doing is what you need to do, which leads us to attestation, actually, doesn't it? So
go for it.
Yeah,
it's almost like I saw that coming. So let me just give a brief view of how you might describe attestation. The way I tend to think of it is, it's all very well your cloud provider saying to you, oh yeah, if you give me your workload, I'll put it in a safe space in a TE and it's going to be great. I'm not sure I'm entirely happy with that. Yeah. What attestation does is allow the underlying hardware, which is providing the actual TE, to do a measurement of what you've put in there. And for that to be fed back to you. Now, exactly how they do it depends on the different technologies, but that's the basic. You get a cryptographic assurance from the hardware that what has been set up is what you expect, and what's been put in it is what you expect. So you can have those assurances that, okay, I'm now happy that what comes out of it or what I put into it is protected in the ways that I expect. Is that a decent description? Have I missed stuff out?
Yeah. Just one more aspect is attestation provides you that assurance that you're running on a genuine AMD, ARM, Intel, Xilinx, right? Whatever it is, right? And they are standing behind the protection claims, right? Which is great for cloud service providers, right? Because one of the things they want to get out of is that, I'll call it liability, but let's call it responsibility, right? For the protection of data, right? All the cloud providers do a lot to ensure the security of their data centers, right? But they don't really want to be responsible for your data, right? You as a user, right? They'd like to just operate as a utility in many cases, right? Just provide MIPS to everybody, right? And the best throughput, right? Focus on that because that's what they do fantastic job as, right? But in terms of protecting your data, they like to be able to say, hey, go talk to AMD, go talk to ARM or Intel, right? They stand behind what their hardware is doing.
And they're going to charge you more for using TEs. So it works for them too.
Well, there's one other important point, though, which I think should be emphasized, which is common, I think, across all, at least the current set of TEs, which is that you typically start a workload in a TEE without any secrets in it. It starts in plain text, if you will. And it's not until after you successfully complete attestation that you can feel confident to actually put secret data in there. So you might think of this as you ask your favorite cloud to start up a VM, and it boots up a Linux image, and you want to make sure that everything is all looking good before you give it the key to your hard disk to actually start processing secret data. And I think that's common across all of the TEs today, is that they all require starting from a very vanilla image that has nothing in it. Then you do attestation, then you get secrets.
To some degree, attestation is the ability to say, I can trust the technology. I don't need to trust the entity.
Yeah, it's the established trust mechanism. Yeah.
Okay, so a question came in a while ago, and I was saving this up. I'm because I was trying to think of how to use it. Maybe the simple question is, what do the spooks think? Here we are talking about. Okay, I have the ability to completely contain code, completely contain data, I can completely obfuscate my storage to some degree. There's a lot of entities out in the world that probably aren't all that excited about it. And now this has been true all the way back to the TPM days, but what's the what's the reaction from the, from the government entities that say, well, no, maybe I want to look at that? Anybody want to field that?
Yeah, go ahead, Mike. You start.
Oh, thanks. Yeah, great. I'm going to turn the other way around and say that they're desperate for it.
Yeah.
They really need this technology themselves because they want to be able to put stuff in the cloud or in embassies or in vehicles or in airplanes or whatever it is, and protect it in these sorts of ways. And so actually, it's really important to them. And, these technologies, it's possible to provide the same sort of protections yourself if you're really paranoid and not be out on the cloud. So if you're that paranoid and you're a bad actor, then you can probably come pretty close to this yourself if you're very careful. So I don't think that it's a huge change in the way they look at the world, and I think that from their point of view, the benefits are likely to outweigh the disadvantages. Now, I don't speak for them. I haven't spoken specifically to any US or in fact any other government agencies on this particularly, but that's the feeling I've been getting.
Yeah, I think that's kind of what I see too. And certainly there are governments, even I'll pick on Germany as an example, right, which is well known, right, for their privacy regulations. But they're not alone, right? Much of the EU, even countries in Asia Pacific region, right, and now even in North America, right, are starting to require these types of technologies and for certain use cases, for protecting the information of their citizens, healthcare data, things like that.
In fact, that leads us really nicely to another question I hear quite a lot about is what about regulators? How do they feel about this sort of stuff? What about CCPA? What about GDPR? What about maybe FedRAMP? And the answer to that is, at the moment, because this is early days, as far as I'm aware, none of them have specifically said, as if you use TEs or if you use confidential computing, you're good to go in the cloud in ways you weren't before. But I think we're definitely edging towards that. And that's one of the things that the Confidential Computing Consortium is interested in, is talking to the regulatory bodies about exactly these sorts of things. Because, again, this plays nicely into the storage, cloud storage question, because a number of things that you'd love to be able to do in the cloud and have local storage or local cloud storage, should we say, can be very difficult because of exactly these problems, where if you have to be doing your processing in a box that you own in Germany, but you want the data to be stored in the US or Australia, even if it's encrypted, that's really difficult. So I think actually the regulators are beginning to take notice, and it looks really interesting from that point of view.
Yeah.
So do you think this ends some of the data fence requirements that are currently exist?
I'm not sure it'll end them. I think it'll change them, because people think about things in very different ways. And even if it doesn't change the data fence requirements, it may be that you can now go to, let's say, all of the continental US instead of just machines that you own in your city, or all of the EU instead of just Germany. I honestly don't know. I don't speak for the regulators, but those are the sorts of things that become possible, which really haven't been until now.
Yeah, we've been talking a lot about cloud too, right? But there's kind of another angle to cloud, right? That where confidential computing really comes into play too, right? And it's related to the regulatory issues that we've been discussing, right? Particularly in the areas like in medical research, right? So Intel has some collaborations with University of Pennsylvania Medical Center, for example, and this is just as an example, right? That they're doing some really interesting research, but per regulations, they're with all the institutions, all the medical institutions that they're doing research with, they're not allowed to share data, so they can't move all that data to the cloud, even with confidential computing, right? So confidential computing hasn't helped them there. But what they can do instead is to load their data in their machine learning models, right, their analysis models, right, into confidential computing capabilities, trusted execution environments, right, at each institution. And now each institution can compare the attestation, right, to make sure that they're all running the same analysis, that it's valid data, right, the integrity is assured, right, and now they can aggregate the results. And so now all, for the first time ever, really, right, all the medical institutions get the benefit of sharing the analysis over a much larger set of data. Right?
I think
something that they just couldn't do before.
Multi-party computation models,
yeah,
testing in the future.
Hey, David, I'm going to bring you back into this. Although I probably should have started with Ron because it was the Intel CPUs that were the problem. But there was a question from the audience. We were using CPUs with speculative execution, out of order, VM task switching, other things like that for quite a while before suddenly somebody realized, hey, there's random data laying around that I can go take advantage of. Is it, and again, I'll flip the question a little bit, is a TEE a way to help solve potential future hardware problems, or are we introducing potential future hardware problems?
Well, I see TEEs as being additive to the security world. We like to talk about things like defense in depth, right? And we're used to that in all aspects of our lives, right? Our cars have seat belts, they also have airbags, right? And confidential computing and TEEs can be another airbag, right? They can help prevent against unknown issues, whether they're hardware issues or software issues. And that's one of the great things, I think, is that we have an extra layer now that you have to get through. If you think about a typical virtualized environment today, if there is a bug in the buffer overflow type bug in the hypervisor, that might be game over. It might mean that everything on that system is now lost. And if you're using TEEs in confidential computing, that's not enough anymore. You now have to go a step further. And so if there's a 0-day in there, then you now have that additional layer of protection still there. So, I can't say that TEEs will, solve every security problem, because they certainly won't. But it is just another layer, and I think that that's how any realistic enterprise system has to be built, is security through layers.
Yeah, and one of the things I think that it does. I mean, we should not be pretending here. No security is perfect, right? And a TEE will not protect you from an attacker with long-term access, with possibly invasive access to a system. But it protects you against loads and loads of other things. And one of the important things is that TEEs have been designed with particular threat models in mind. So when you're asking the questions, what protections are provided, you can say, well, these are the ones that TEEs help you with, in ways that something like containers probably weren't to start with. Now that's been added on to some degree, and VMs are more mature, so hypervisors and stuff have a better view of these models. But I think from the beginning, TEEs have been thought about with security in mind, and therefore it's been planned, and the threat models and the mitigations, etc., are laid out, so we know what they are. So it's easier to make statements and have assurances, and I think that's what we come down to, is about assurances. Ron, you're nodding.
Yeah, no, exactly, and I agree with everything David said as well. I should point out, right, that Jim, since you mentioned this, right, every CPU, right, ARM, AMD, Intel, right, was subjected to some of the speculative side channels, right. Intel had a few more variants, right, that were unique to us, I think, right, unfortunately. But side channels go back to the mid-90s, right? At least in industry, right? And they're not just speculative, right? They're differential power analysis attacks, right? That were made, very famous back in the mid-90s. As an industry, we really didn't do a good job of addressing a bunch of those or taking them seriously, right? Until Spectre Meltdown, for example, right? But taking us back to confidential computing and trusted execution environments and how that can help, right? I think Mike also mentioned this, right? That attestation capability, right? We can't underestimate the value of that, right? Because what you want to do now is that any mitigation technologies, because we're all working hard to mitigate all side channels as much as we can, right? But you also want to ensure that your workload has those mitigations enabled, right? And attestation provides that capability. It allows you to verify, right, that your system has been set up or your workload is running on a CPU where only you're using this particular core, right? So you don't have to worry about hyper-threading issues and sharing, right, and speculative execution issues there. Or you may have some particular software stack that mitigates some of the side channels, right? You want to make sure that that software is really running unmodified.
So that was exactly the point I was about to make. If I can go a bit geeky on this, one of the questions that comes up from time to time is constant time crypto, because there are a number of attacks which, based on timing, in how you use cryptographic keys and operations and stuff, and it may be that the T's on their own don't provide you with an answer to that,
right?
But there are possible implementations within the T. It's going to have to be quite low level, in conjunction with other parts of the system, even possibly, which may allow you to do that. I think actually one of the other interesting questions that I'd like to push back to the vendors, we've got ARM and we've got AMD and Intel here, is questions of clock time. One of the difficulties for T's is how you measure real clock time, particularly wall time within TEs and cycles and stuff. So there are some complex things, and I'm absolutely certain, in fact I know because I've spoken to a bunch of the engineers, that we've got clever stuff coming in the future to address some of these sorts of issues. But as you know, as David said at the beginning, this is not, it's about depth. We have raised the bar so much with these, if we use them right, that it's a great new set of weapons in our arsenal, if you will, our armory.
Yep. You know, the one thing I'll throw in, and by the way, I should throw in the disclaimer, I'm a former Intel employee, and
as am I.
Yeah, so yeah, everybody works for after a while. And back in the day when I was in strategic planning and we were actually looking at some of this, we were really focused, or in fact, a lot of the industry was really focused on performance first. And so there were a lot of conversations on, well, we could do this, but this might impact the performance. Yeah. My speculative comment here is I think the conversation has changed in a lot of the design, and this is an example of what we're talking about. Trusted execution environments and confidential computing seems to be an example of this. We're really thinking protection first, and then we'll figure out how to deliver the performance and deliver the capability around it. Would any of you have any comments on that?
Yeah, I mean, I sort of agree. Performance is absolutely important. So, you know, security is also important. But, you know, if you have a security solution that causes your application to run 10 times as slower, that's not practical. You know, that might be fun in theory, but, you know, I know that we at AMD certainly focus on performance quite a bit, because we want customers to be able to turn on these features and not have a major impact on their business. You know, yeah, it's not gonna be free. It might cost you a couple percent, 5%, I don't know. But, you know, if it's costing you 5x your performance, and that turns into 5x your cost because you're paying for CPU time, that's not, you know, acceptable to me. So I think that it is a balance that we have to strike. I think that that's an area that we're going to continue to focus on going forward. It's one of these things where, you know, we really try to get security right first, and then we're going to optimize for performance. But if you look at the current offerings out there, I think that they do put a significant emphasis on performance.
Yep. Yeah, I agree. Absolutely.
There's a well-known triad in security where they see, if you think of a triangle, at the top you've got security. On one side you've got usability, and the other side you've got cost. You can have two of the three, but you can't have all of them. And I think that the approach that I'm seeing in the moment in the industry is that we realize that we need to balance that and say we need to be usable, we need to be as secure as possible, and cost may be what takes. Now, it doesn't mean that necessarily translates into the cost for the consumer, but the reason that some of these technologies have taken a while to turn up in the market is because the Intels and the AMDs and the ARMs and the IBMs of this world have taken the time and spent the resources really to think it through. So this is why it's taking a while for this stuff to get into the market, but it is getting there now, because you guys know that it has to be usable, but it has to have decent security. And usability is partly about performance.
So we've done a reasonable job geeking out, but I want to make sure that we're talking that we're answering a pretty broad set of questions. And so I want to kind of throw it to, yes, this is a new technology, but let's start talking about the value proposition that we're really talking about from a deployment perspective. So, it appeals to the geeks because we all love this stuff. Why or how is this going to appeal to the CISO or even the CIO in terms of a thing that, an arrow that I have to have in my IT quiver?
So I hope that in 5-10 years, it won't be a why would I deploy on this? It will be a why wouldn't I deploy on this? Because it's going to be so easy and the performance and all that sort of stuff. But for now, I think customers, or people, tenants, should we say, of clouds, or people who are thinking about deploying this, need to ask themselves, what are the crown jewels of my organization? Is it the customer data? Is it my crypto keys? Is it my AI models? Is it my pharma research? Is it my my military records? What is it that is the crown jewels? And think about how they architect their applications to protect those bits. Because to start with, now, in the next 2 years or so, it's going to be kind of difficult to roll out. And you need to think, okay, how am I going to store that? How am I going to transport it? That data in use, data in transport, and data at rest, that triad there. So I think that it should get to why wouldn't I? But for now, it's what is the stuff that keeps your business going, which currently is really expensive to do because you have to do it internally, but would be cheaper if you could do it in the cloud or on the edge, for instance. That's how I approach it.
I think maybe I'll add to that a little bit. We have to recognize too that computing in general and workloads, right, are changing, right? So it's not just the traditional enterprise application anymore, and whether I should move to the cloud, is it safe or not, right? That's still an issue, obviously, right? But with technologies like 5G, for example, that are really pushing the bandwidth issues, you're seeing compute start to move out to the edge, right? So the cloud, the definition of cloud is changing. It's no longer this mega data center only, right? It's these regional data centers. It's the server hanging off a telephone pole so they can talk to your Tesla, right? And direct you in the right place, right? All of these things are going to be running mission critical workloads, right? They need to be protected. At the very least, you need to make sure that the integrity is there, right? That the right code is running. It hasn't been modified, right? So confidential computing is going to be used everywhere, right? From embedded systems to HPC systems, right? I don't see an area where it won't be used.
Okay, David, any thoughts?
I agree with all that. I mean, I think that at some point it might, become a regulatory requirement, right? As Mike talked about earlier. And so that might change the equation. I think there's certainly an aspect of, you might feel that there's some data that you only feel confident dealing with on-prem today. And maybe confidential computing is enough to change that equation. Now you feel confident about doing that in the cloud. But also, it's another tool. And at some level, I mean, if you can make it work and the performance cost or whatever doesn't bother you, then why not have the most security just in case if something happens? I mean, you never know what's going to come out tomorrow, security wise. So
IT's used to a belt and suspenders approach, so this is another opportunity for them to add another thing to the trousers, so to speak. So let's talk about final thoughts, and I'll actually go to all of you. I'll start with you, Mike. Final thoughts. What would you like to make sure the audience is walking away with from this conversation?
You need to start thinking about this. You need to start thinking about it at two levels. One is the CISOs, to think about risk. Think about what the things you care about. What are your crown jewels? And the other is for your techies to start seeing what are the tools that they might want to start using, and be aware those are changing, that startups and open source and all those sorts of things, that you're going to be seeing loads of stuff coming, and more stuff from the hardware vendors and all of that. Start looking now, because it will give you a huge leg up for when your regulator says this, or when you suddenly want to move some stuff into the cloud, or when this, that, or the other. This is an opportunity for competitive advantage for your company. think about it now.
All right, David, I'll go to you next.
Yeah, I would say, you know, start talking to your solution providers, whether that's cloud service providers or you know, private hypervisors, whatever you're using, about this technology and their plans for it, because it's happening. I mean, there are offerings that are starting to come out, and you know, it's important to find out what you need to do to make your workloads compatible with these, identify what the right workloads are, and work with those solution partners to make that happen. You know, I would like to say it's going to be as easy as a checkbox. Maybe in some cases it will be, but probably it's going to require a little bit more work.
Not for now.
Yeah. And Ron, bat cleanup for us here.
Yeah, just double down on everything Mike and David said, right? 100%. Maybe bringing it back to storage, since we probably have a lot of folks, right, interested in that watching today. I would say that, you know, you guys know better than we do, in fact, right? How storage and compute are changing, right, together, right? Whether it's, you know, the memory storage hierarchy, right, the distributed computing aspects of it, data moving around, right? You guys, you know this much better than we do, right? But compute is also finding its way into all of these elements, right? Whether it's a smart NIC or a storage device itself, right? You're gonna want those. Your customers are gonna want those assurances that come with something like confidential computing, right? In some cases, it may be the confidentiality aspect, the protection. In other cases, it's surely going to be the attestation capabilities, right? Proving that the right code is there, right? So from secure boot to, you know, while data and while code is in use, all of that, right? But yeah, reach out to us, right? We're all available. We'd love to learn more about what you do, right? And how these technologies are going to impact you.
Yeah, we need your use cases. That's really important.
Yeah.
Come to Confidential Computing Consortium. Talk about your use cases. There's a forum to do that. The User Advisory Council would love to hear that. Get in touch. You don't even need to pay. That's a free thing. So there we go.
You can pay me, but yeah.
And I'm the treasurer, so I should be asking you.
Hey, moderately free. That's good. There's a couple of questions we didn't get to, and what we will do as usual with our SNIA webcasts is that we will be doing a Q&A blog. So check out the SNIA blog for that. I did want to advertise, though, our next webcast, the Confidential Compute Protecting Data in Use, June 23rd, 2021, and you can see the registration link there. And like I said, I believe that that's also available in your in the downloadable section. If you do have some additional questions, you can always ask those. And like I said, we'll get that in the Q&A webcast. I would certainly like you to also use that rate button along with the comments. So feel free to rate this webcast. Please, let us know what you thought. Put in some comments in terms of what you'd like to see. We view this as a series. We're going to be talking about confidential computing and how it's going to be useful. And we'll provide that Q&A. You can follow us on Twitter. I certainly would like to thank all three of the very smart presenters. It's easy to be dumb when there are three really smart people hanging around. So, gentlemen, thank you very much for your time. Audience, thank you very much for your time, and we look forward to seeing you on a future SNIA webcast. Have a great day, everyone.
Thank you.
Thank you.
Bye.
Bye.
Bye.